All right. Welcome to Galois Tech Talk series. I'm going to go ahead and turn it over to Joe, who's going to.
So, Zdancewic from the faculty at Penn. With Galois here, but through August, where thanks.
Great. Thank you all for coming, and let me also thank Galois for inviting me to come for this summer, and also for the sabbatical. I'm having a great time so far, and this is a really wonderful opportunity. So thank you all for having me. So as Joe mentioned, this talk is going to be about a long-running project that has been going on at Penn for several years now, about trying to verify LLVM programs. And two things I want to say up front. So first of all, this is joint work with many, many collaborators. I hope you can see the slides. They're maybe a little bit too light in this room. Over many years, and without all of these people, I wouldn't be able to stand here and tell you about this. So that's one thing. Thanks, collaborators. The other thing is this is sort of cobbled together from many different kinds of talks, so it's sort of the greatest hits of our Vellvm project. And so the technical depth is a little uneven, and in fact, at some point, I ran into the issue of trying to merge two slide decks where one of them was in this wide format and one was in the 4:3 aspect ratio, and I actually just switched PowerPoint projects, so it's too painful. And that said,
Stephen, can I interrupt
yeah.
just a minute? People on the line, could you mute yourself? We're getting a lot of keyboard noises and things like that.
So if there's anything here that piques your interest, feel free to ask me or catch me afterward. This is just a starting point in the conversation. Okay, so verifying the LLVM, I don't assume that all of you know what the LLVM is, but sort of the 2-minute summary is that it's a modern compiler infrastructure that was came out of academia. It was Chris Latner's master's thesis at the UIUC, and it has evolved into this big open source project that is widely used both in academia and in industry, notably by Apple. And what it is a compiler intermediate representation plus a suite of tools for working with that is able to process many different source front-end languages and do many optimizations and produce many target executables via JIT or code generation. And for the purposes of our research project, the fact that many of the interesting optimizations that are done at the LLVM IR take place in kind of this core representation, which is the LLVM IR itself, which is a typed SSA language, and in which many of the optimizations you can see as transforming that language to itself. So if you want to understand this compilation pipeline, putting your effort at that spot is a good target, and that's basically what we're trying to do. So the idea of Vellvm is to take the sort of core bit of the Vellvm of the LLVM and formalize it. And we do that by building formal semantics in the Coq interactive theorem prover, and then inside that development, providing tools for things like creating simulation proofs and reasoning about the semantics. But we also have this idea that you could, for instance, implement some interesting program transformation at the LLVM IR inside of Coq, and then extract it to plug into the actual LLVM compiler so that you could have a high confidence program transformation. And so I'll say a little bit more about this, but some of the things we were motivated by are things like memory safety transformations and security applications for C code, where you really want to be sure that you're not making a mistake. But we've also looked at many other optimizations. And so just to give you another picture of what this framework looks like. So first of all, the LLVM framework itself typically starts with something like C source code, translates it via some front end to this LLVM IR, and then goes through a series of transformations to reach this target. And what we're basically doing is inserting a way to inspect that LLVM IR via OCaml bindings, and then building on inside of Coq the machinery needed to work with that IR, giving it as semantics and doing the appropriate metatheory. And then you could take, for example, a program transformation that you've implemented and prove something interesting about, and extract it into an OCaml program that is then able to interact with the regular LLVM pipeline. And so when we started this project, it was inspired by the wild success of Concert, which had just become a big splash on the scene. My PhD student, Zhenzhou Zhao, who is really the progenitor of this work, took a lot of inspiration from that project. You'll notice that we're being a little bit less ambitious in one way here, which is we're not trying to verify the entire compiler pipeline. So we don't get an entire end-to-end correctness guarantee like Concert gives you. But instead, we decided to concentrate on applying these kind of verification techniques to a real-world IR. And in the future, that's an interesting possibility would be to connect up our LLVM semantics with perhaps verified backends, perhaps even to one of the Concert levels. But for now, we're satisfied with getting improved confidence with program transformations. Okay. The other thing I should say is please ask questions during the talk. And I probably have too much material, so I'm going to end up maybe skipping through some things quickly or jumping ahead in the interest of time. But please feel free to ask questions, or I'm happy to tell you about it more later. Okay, so for those of you, actually just by show of hands for a local audience, how many of you have seen LLVM IR before? Okay, maybe half. So I'll quickly go through this. So just to give you a flavor of what this IR looks like, it's sort of one step above assembly language. It's kind of a traditional control flow graph machine compiler representation where you have control flow graphs where the basic objects are blocks of code. Each instruction is basically a binary operation, and the blocks are connected into the graph by branches and jumps. And then LLVM uses what's called static single assignment, which is basically assuring that these control flow graphs programs are kind of a functional programming language. So each of these variable definitions happens only once in the control flow graph, and this means that you can sort of think of these things as more like let binders, if you're familiar with Haskell or OCaml, than to actual variable assignments. And the only slightly interesting twist to that is because these are control flow graphs, SSA introduces this idea of a phi node, which basically is sort of a control-dependent operation. So in this particular example, the meaning of a phi node depends on which dynamic branch you took to get to that location in the code. So if you jump to this loop entry point from the loop itself, then you would get the value R5 at that point in the code. And otherwise, if you came in from the entry, you would get 0. So it's sort of a bookkeeping trick for dealing with cyclic dependencies in the control flow graph. And there's a little bit of a wrinkle to the semantics when you write these things down to deal with phi nodes. Okay, so that's LLVM from in a 2-minute introduction. So what do we do with that? Well, we're encouraged because the LLVM IR semantics are more or less like a functional programming language. So these variable definitions are like lets. With a little bit of squinting, you can see the blocks as sort of mutually recursive functions, and phi nodes are sort of calls or tail calls in these graphs. And so writing down semantics for these things, you can write them in several different ways, but we're taking inspiration from some early work by Andrew Appel and earlier by Galois, where we think of these things as functional programs, except, of course, they're not pure. So a lot of the difficulty of LLVM comes from things that I haven't really mentioned, which make it, at least the compiler writers assert are important for doing important optimizations. Or for handling the fact that LLVM itself is intended to be an IR that can generate code for many different target architectures. And so there are some things that are just target-specific behaviors which are sort of underspecified at the LLVM level. So that leads to a couple different notions of undefined values or behaviors. They have this concept of poison for sort of what happens when you do an illegal operation. And of course, these programs really aren't pure. There's a whole memory model, and of course, system calls. And LLVM itself is only just now starting to develop what its semantics means in the presence of concurrency. So there's many other things. I guess the other slightly interesting thing, which is a little bit easier to deal with, is that LLVM has support for types. Most of the time, the types are used just to help the compiler structure the data in memory, but it does provide a notion of essentially C-style structs and recursive data types and things like that that the compiler can use. Okay, so we know how to do things with this, and I'll say a little bit later how we're starting to even do this kind of reasoning a little bit modularly. And so Vellvm. So Vellvm, as I said, is trying to give a formal definition of this and to apply that definition to interesting program transformations. And so I thought it would be useful to take a kind of high-level view survey of Vellvm. So I'll first tell you about the good things that we've managed to achieve. And then I'll tell you about some of the bad things about our original Vellvm development. So to give you a little more context, this project started in 2012 or so with my PhD student, Jen Zhou. We built this big infrastructure, used it to prove lots of things, and then for various reasons that I'll explain in the sort of bad parts of Vellvm, we've decided to take a step back and do another version as part of this DeepSpec deep specifications project that I'll mention later. But the good things we were able to achieve are what are encouraging us in that direction. And in fact, I like to think of sort of the bad and the ugly things about this as just research opportunities. So if you have any ideas about any of these things, I'm happy to chat. Okay, so what are some of the good things? So kind of at the high level, I actually got into verifying LLVM code because of another project we had going at Penn, which was about retrofitting memory safety properties into legacy C code. So the idea was we have a lot of existing C code. We know that it's not going to be memory safe. At the time, we were looking at both hardware and software co-designs for ensuring the safety of C programs. And the software version of that was implemented in LLVM as a program transformation that took LLVM IR and added essentially array bounds checks and things like that. And then we started thinking, how do we know we didn't miss any of the corner cases? And, these var args are really a pain. How do we know we got that right? Could we somehow prove or give a formal model that what we were doing was correct? And so that was sort of the original motivation. And I'll sketch how we tackled that in just a few minutes. But we also looked at a number of other optimizations that are available in LLVM. The most impressive of which was this mem to reg pass, which is kind of register promotion pass. I'll also sketch a little bit about that. And along the way, we looked at a number of smaller but important optimizations and a few other things. More recently, we've been looking at how to deal with the memory model and some sort of thorny semantic issues for these low-level languages with things like into-pointer casts and concurrency, and I'll touch on those a little bit as well. Okay, so those first two things, reasoning about memory safety or reasoning about optimizations, basically boil down to reasoning about transformations of these programs in SSA form. And in order to do that, our approach was rather standard, right? We give a dynamic semantics to the LLVM IR. We use LLVM itself has a notion of a static semantics about what LLVM programs are well-formed. That has to do with the shape of these graphs and which variables are in scope. And we observed that you could sort of generalize the standard kind of safety properties to prove other interesting safety properties for things like the memory safety proofs. And we use sort of two techniques in those endeavors, one of which is basically to is what we use for SoftBound, which is to give sort of a non-standard semantics to the language, one that's sort of correct by definition or sort of oracularly correct, and then show that the code instrumentation you've done at the real LLVM level simulates the kind of correct transformation. And the other thing that we found useful is decomposing complicated program transformations like our mem to reg pass into many, many, many tiny little transformations that are much easier to reason about in isolation. Of course, there are some trade-offs for that I'll get to. So let me talk about how we do this memory safety pass first, just kind of at a high level. So the original Vellvm semantics provided a whole suite of definitions for reasoning about these programs. Because of the things like undefined values and underspecification and undefined behaviors, our original semantics included a kind of non-deterministic model of computation where the program could, there's some kind of timing remnant in the slide, sorry about that. The program could non-deterministically do many possible things, which is more faithful to the LLVM semantics, but hard to reason about because of the non-determinism. So we also showed a deterministic refinement, and we in fact proved that deterministic refinement was equivalent to a particular interpreter that we could extract and run. And in our original Vellvm work, the way we validated our semantics against sort of the existing LLVM compilers was by running our interpreter against the same test suite that they did to at least know that we agree on those cases. Nowadays, we're looking into collaborating with John Rager's group of using some tool like something like CSmith to do more sort of end version testing against our semantics and other LLVM compilers. And we provided sort of a small step and a number of sort of big step operational semantics that would let you kind of ignore unimportant details like skipping through a whole block. Okay, so how do we use those kind of operational semantics to prove some properties like these memory safety? Well, here's basically the idea. So let's recall that kind of the standard programming language tool for doing safety properties is some kind of preservation in progress theorem. So the basic idea is we have a notion of well-formedness for LLVM programs. LLVM programs give you only sort of a weak notion of well-formedness, which is all the variables, when you use them, are in scope, or they're defined before you reach them dynamically in the program execution. So sort of there's a scoping mechanism that's defined in terms of the dominator relation of these control flow graphs. And that provides a useful notion of well-formedness that we can prove properties about using sort of standard techniques. So basically what we do if we want to show that if we have some function f and we run it, then it never becomes undefined in the sense that our machine semantics doesn't have a value. And so we prove that by showing that the initial state is well-formed and that this well-formedness predicate is preserved by each small step transition. So if in the program f, the state sigma transitions to the sigma prime, and you start in a well-formed state, then you end up in a well-formed state. And of course, we have some notion of progress, which says, well, in any well-formed state, you're either done and the machine has terminated in sort of a good expected behavior, or you can take a step and keep going. So this is all kind of standard PL stuff. And we adapted these techniques to LLVM, where the well-formedness predicate basically also takes into account the scoping that's influenced by the dominator structure of the control flow graph. Now, so we're going to use that basic structure to prove our SoftBound instrumentation pass correct. How do we do it? Well, we implement it as an LLVM pass, so this is just a code in Coq that translates LLVM IR to LLVM IR. And the goal here is to basically rule out a class of memory safety violations. So you never read from unallocated heap locations, and you don't read outside of the stack frames. And in fact, we enforce things at a fairly fine-grained level. So in C, you can have sort of nested structs and nested arrays and things like that, and we can enforce boundaries at those levels as well. So this is a non-trivial program transformation at the LLVM level. It's a good test of our proof techniques, and also we cared about it because of these other reasons. In particular, we had, of course, a C++ implementation of SoftBound that we were working on at the time, and we kept running into corner cases of, did we get this right? Did we get this right? And in fact, in the end, our formalization in Coq suggested some nice ways to simplify the C++ version that I'll mention briefly at the end. Okay, so just to give you a slightly deeper sense of what this looks like, so here's basically what the LLVM pass is supposed to do. So on the left here, we have a call to malloc, which allocates, in this case, it looks like a 10 character array or something. This get instruction, get element pointer, is sort of LLVM's way of computing indices into structured data types. So this is where you compute a pointer into memory. And then maybe we use that, which is Q, and then we store some value into Q. So what the SoftBound pass does is for every, for code that looks like that, it will instrument it with a bunch of sort of metadata that is propagated. So first of all, it will add base and bound information to every pointer in the program. And then that's not sufficient. You also have to sort of propagate that metadata everywhere the pointer flows, both as function arguments, for example, or if you store the pointer into memory, you have to somehow know where to find the base and bounds information. And then when you calculate pointers from other pointers, like in this case, the get element pointer instruction here propagates the metadata. So anytime you pointers around, you have to also shuffle the metadata around. And then anytime you do a dereference, like a store or load, you would add some code that does an assertion to make sure that the bounds checks are correct. And of course, we had many optimizations that would try to minimize the overhead of doing this, and the LLVM code itself could be optimized. But this is sort of the basic idea of what we were trying to achieve.
And do you envision that those things would stay in the code when you run it?
Yeah, so the intent of SoftBound was to make it low enough overhead, reasonably enough overhead that you could just leave this on after you were done. And we were able to, so there are different modes of use. I'm happy to go into more detail about this later, but if you care only about instrumenting stores, for example, as opposed to both loads and stores, you can get the overheads down to I don't even remember now, and it's changed since the talk, but not more than double, which is pretty expensive for many applications, but fairly reasonable compared to other costs, other techniques.
That is, the code runs half as slow.
Yes, but that's with, I believe that's with all of the, like, including the stack and maybe also checking loads as well. I have to actually go look at our paper. It's been too long. So anyway, the point of this bit was to prove that we didn't miss anything. And so here's how we do that. Well, first of all, one of the key ideas behind the SoftBound system was that the metadata that associates the pointer, that goes along with each pointer lives in a sort of a shadow space. So you can imagine every location in the real memory having a shadow location where the metadata would be stored. And there's this important invariant, of course, that you can't sort of have user code that you're instrumenting that corrupts the metadata in some way. So you have to make sure that that doesn't happen. And of course, there are many optimizations you can play to, you don't actually need a shadow memory location for every real memory location. And we explored a bunch of those things. But from the point of view of the proofs, sort of this disjointness criterion is really important. And then, there's many invariants that you have to show are kind of satisfied as your code is executed. So how do we prove SoftBound correct? Well, first we define this instrumentation pass as a Coq program transformation. So it takes LLVM IR code and produces LLVM IR code kind of like I showed you. And we have to lift that to not only the kind of the static code, but also to the dynamic states. So we also have to be able to say how would a memory be instrumented and so on. So we can kind of relate dynamic states of the machine. Once we do that, for the original LLVM semantics, we can characterize in Coq a predicate that talks about the behaviors we want to rule out. So you can think of this as saying, in some program F, we know that there's a memory violation in this state. And then what we can prove, what we do is we basically clone our LLVM semantics and make it correct by construction. So I'm writing this with sort of steps to SoftBound. And this doesn't have anything to do with the LLVM code that we instrumented. It's just sort of a fictitious machine that is always guaranteed to catch these memory safety errors. So you can prove a theorem about this non-standard operational semantics that it will never run into a memory violation. And then what you do is you show essentially that the instrumented code simulates that non-standard semantics. And you can do that using kind of standard simulation techniques where you have two languages and you have to show that the states line up. And the invariants get pretty hairy because the memory relations are quite complicated. But it's doable, and we can prove all of that in Coq. And so basically the idea is that if the instrumented code runs, then I think I'm missing SoftBound annotation on one of these. But basically the idea is the instrumented code implements the behavior of the specification, which is just sort of, and the specification is itself an entire non-standard language semantics. Okay, and so we did that, and we actually found many bugs in our C++ implementation that we fixed. And the other cool thing that came out of that was, it's obvious in retrospect, but our first attempt at passing metadata associated with pointers and function arguments was to rewrite the function calls so that they took extra parameters for the base and bound information, which is possible, but not very robust to other kinds of things. You have to make sure you've changed all the call sites as well, and it doesn't work very well with var args and things like that. So the obvious in retrospect idea is to have a shadow stack that you also mirror whenever you're passing arguments to functions. It wasn't obvious when we did the original implementation, and in fact we thought of it, but thought it would be too costly because every function call you're going to be manipulating the shadow stack. Turns out that with a little bit of tweaking, you only, of course, need to manipulate this shadow stack when you're pushing pointers around, and the overhead's not that bad. In fact, it was much better than the rewrite the function arguments because that interfered with register allocation and all sorts of other things. So sort of the proof theory, the proof version of this, which is where we came up with this idea of shadow stack, since we had to build these simulations anyway, suggested a good implementation for our, and that's what's in SoftBound nowadays. In fact, you can still get SoftBound as part of the LLVM release. Santosh Nagarakate, who is the PhD student who worked on that, still maintains it. Okay, any questions about SoftBound? I'm going to switch to a different optimization. Yeah?
So what if you have a program that only works if there's a memory violation by using out of the memory, then it shouldn't really do with the transformation of the program?
Probably not. So this would be a program that somehow could only be correct if it was memory unsafe would be ruled out by our by SoftBound. I don't know of any. Well, maybe there are programs that are useful like that, but I'm not sure.
You think of a program that produces part of a say, buffer just above the bubble bound, but it works if you don't have to check that you get out of the boundary. But when you try to transform it,
yeah. So I mean, you could certainly imagine code, for example, that takes the top of the stack and treats things past the top of the stack as kind of a scratch space. We could adapt the instrumentation pass to allow that behavior, or if you know there's some fixed zone after the top of the stack that is being treated in that way, you could adapt the instrumentation. But in general, we would be conservative and reject this.
it's more interesting in finding out how you detect it.
How would you? Well, so we could. So in our instrumentation, we have to treat the stack pointers as pointers with metadata associated with them. And so, if you maintain some invariant about the stack frames, you could know as part of the instrumentation that some zone past the top of the stack was allowed, for instance. Yeah. Yes.
Maybe you said it, but how did you deal with pointers stored in dynamically allocated like structs or whatnot?
Yeah, so that actually just falls out naturally from the meta shadow space, because anytime you write a pointer to the regular heap, its metadata gets written to a corresponding location into the shadow heap. And so if you have a linked list of pointers, each with metadata, a linked list of pointers in the original program, you'll have a linked list morally of pointers in the shadow space. Yeah? Oh, do things ever get removed from the shadow space? Yes, so you can garbage collect, or you can, anytime you free. So we did have to check for double frees, and there are various constraints that you can. We had so the original SoftBound only did memory safety, what we call spatial memory safety violations, where it was just looking for bounds accesses. But of course, there are temporal memory safety violations, which are things like double freeze, or if you return a pointer to a stack frame that gets popped. With more overhead, we show how to do all of that as well. And so you can actually be what we think of as relatively complete for safety, but that gets correspondingly more expensive. Yeah.
So it sounds like if you need basing bounds for every dynamically allocated pointer, you're basically tripling your memory footprint for every
Yeah.
program.
So it turns out you don't need. You can do optimizations to get rid of that, and we do report on the memory overheads in some of our papers. We didn't experience. So it turns out that there's a lot of non-pointer data in most code. And so it's not nearly close to 3 times the memory. But in the worst case, if it was all pointers in some really complicated graph, then yeah.
So you have some clever way of just it doesn't have to be like if I have a struct with 2 pointers in it and
so
they're
for
12 bytes
arrays,
apart,
for example,
it doesn't necessarily.
you can compress all the metadata to a point, for arrays in certain ways as well. Yeah.
So if you have if I pass a pointer something on my stack to another function, can you do some sort of interstitial analysis to figure out whether that's actually, you don't always need to pass this information around, but...
We didn't do anything that fancy. So his question was if we pass pointers around, maybe sometimes we don't need to pass the metadata because you might not dereference it, or it might be parametric or something, or maybe somehow that it's always going to be in bounds. But we didn't do any inter-procedural analysis. We did, all of our optimizations were sort of local analysis. Like the sort of thing that is really important is once you've checked the metadata for a certain pointer, if the pointer hasn't had any computation done to it, then it's still in bounds. And so you don't need to check on every access, only sort of the first in a sequence until something might have changed. And so that's the sort of optimization that's a big win in this case. Okay, so actually, for the next part of my talk, I want to switch to a slightly different presentation, since, as I mentioned, I was combining two different things, and this is a different aspect ratio. Okay, when I put them together, they just look awful. Okay, so just as a flavor of another technique that we use in Vellum, which I think has also come up again in many different formalizations, is this idea of breaking complicated transformations into lots of tiny, smaller, easier to reason about transformations, and we use that in this mem to reg verification. So mem to reg is an optimization that basically does what's called register promotion. So it looks for these what would normally be stack allocated data values and puts them into registers instead of on the stack if it can determine that that's okay. And so this turns out to be a really important optimization for LLVM performance because without it, basically you can't do a good job of register allocating. And sort of the standard way of compiling C is to introduce many, many allocas. So here's an example of what mem2reg does. So here's a little snippet of C code. And this kind of standard way of doing a front end for LLVM is to, for each variable that you introduce like X here, at the C level, you would create an alloca, which is a stack allocated variable by default. And then you would, for example, initialize X to 0. You would store 0 into the address corresponding to X. And then, the rest of this block is just loading and storing. Every time you need to access X, you load from the corresponding stack slot, basically. So this code is easy to generate for C front ends because they just do this very uniform transformation. Every variable is an alloca. You always load and store, but it would be very inefficient if you actually implemented it that way on hardware because you would be accessing the memory a lot. So what mem2reg does is it recognizes, oh, we never take the address of this variable X. Its address never escapes this little snippet of code, so we can put it into a register instead. And so it will do that by basically introducing temporary variables. And then the main operation that this transformation has to do is to introduce these phi nodes that I mentioned a while ago that sort of talk about how you merge these values due to control flow. So the exact behavior of this isn't really too critical, but basically you should think of this as given some alias information about and escapes analysis about these variables, figure out how to rename them, and then insert these phi nodes to kind of patch up the control flow graph to make sure that it's still semantically correct. So it's kind of a renaming phase. And the problem, so LLVM implements this. We tried to do both a kind of translation validation approach where we would run the actual LLVM translator optimization pass and validate the output. That turned out to be really hard because LLVM wasn't designed with translation validation in mind, so it would basically not keep enough information about what it was doing. And it also turns out that some of the intermediate stages of their implementation break the SSA invariant in ways that were hard for us to reconstruct after the fact. So there's sort of this discontinuity in the well-formedness of the LLVM programs that was hard for us to deal with. So what we did instead was sort of take that standard optimization and deconstruct it into a whole series of smaller optimizations, which are mostly correspond to things that the LLVM already does anyway. So things like eliminating loads after stores when you can identify that that will give you the same value and so on. Dead store elimination. And the nice thing about this is, we prove more or less that this, first we prove that this pipeline of small transformations is correct. So it gives you a program that agrees with the source semantics. But also, like in our experiments, the performance of the resulting code is essentially equal to the LLVM generated code. So you're not losing anything by doing this. It's a slower algorithm. That's the cost because we've decomposed it this way. Our extraction, basically makes the compiler slow, but not the generated code slow. But the other cool thing about this way of doing things is that it preserves the SSA structure at every step of this transformation so that we never, like we can use all of our good invariants throughout the proof. So let's see. I guess I'll just quickly walk through an example of applying this. So basically, if we start with the code on the left, there's a bunch of stages that this goes through. And I'll just quickly flip through it because I want to get to what we're currently doing in Vellvm. So basically, the name of the game here is how to sort of achieve the effect of the optimization while retaining the SSA structure. And so how do we put phi nodes everywhere without breaking SSA? So the idea is we're going to just insert loads at the end of every block and insert phi nodes at the beginning of every block. And basically the idea is that this localizes variable scopes to blocks in a certain way. And we're going to eventually eliminate most of these phi nodes later in a later optimization. So, and then after each phi node, we're going to insert these stores. So basically, we're sort of loading the values that were allocated at the end of each block, putting a phi to record the fact that this happened, this edge was important, and then storing back into the p, the original pointer that was allocated here. So we start with this p being allocated. We add a load. We use the phi node to that's sort of the renaming of the value of p, because now we can use x1 instead of this load. And then when we sort of restore the fact that p is connected to x by using the phi node information in a store. So once we do that, we just go through this series of kind of standard optimizations. So for example, load after store says, if there's a load from a place that you stored and there are no intervening stores, well, you don't need to do the load. You can just remember the value that you stored. So here, for example, we store 0 into p. There are no intervening writes to p, and then we load p. So now we can replace the uses of x1 here by 0. Right? So that's a valid program transformation. I should say this would only be valid, of course, if you know that the pointer p doesn't escape, because if there could be some alias in some concurrent thread, that could change the value. But the whole point of this is you've done that analysis, you know that p doesn't escape or wouldn't be eligible for this promotion anyway. Anyway, so we do the load after store. We can do that several times in this code, and that will, so we do that 3 times, and then we now have a bunch of dead stores because we don't actually need those stores anymore. We never load from p after we've eliminated them, so we can basically cross out all the stores and the resulting allocas. And then it turns out that what you're left with is sometimes useless phi nodes at the beginning of the block. So any block that has exactly 1 edge into it, you can just get rid of those phi nodes by substitution, basically. And any phi node that has the same value on all the incoming edges is also redundant because it says it doesn't matter where you came from, you get the same value. So you cross all of those out, and you end up with essentially the same result. There's a tiny, we're not able to remove quite as many phi nodes as the kind of best LLVM algorithm, but it doesn't affect performance in any of our experiments. So the point of that is it's easy to prove that correct because each of these little micro transformations is pretty obviously correct. That's basically the proof technique. And we prove each of those little micro transformations correct by another, basically instantiating that kind of safety transformation technique that I mentioned in SoftBound with a slightly different set of formulas about what invariants are being maintained. And so we can kind of do a bunch of these different optimizations more or less the same way by picking sort of appropriate safety invariants for, say, dead instruction elimination. We prove a preservation and a progress theorem and so on. So the proof of correctness is just then the composition of all of this. And that's actually where the overhead in terms of our compiler implementation comes from, because since we actually extract the code that's based on doing all these micro transformations, a single, our version of memdredge will kind of maybe take a lot of extra overhead if it's not implemented. Like basically you want to fuse together all of these transformations into a single pass over the abstract syntax rather than a bunch of iterated passes over the abstract syntax. And we did a bit of that just to make our lives so we could run it in a reasonable amount of time, but we didn't do any real optimization. So that it's I think usually about it's usually about 3 times slower than mount to edge, if I'm remembering correctly, but you can also construct sort of pessimal control flow graphs where our algorithm is like 300 times slower, but they're sort of the standard, really hard to do this algorithm on. Okay, anyway, so you can prove correctness of those things. All right, I'm going to switch back to, oops. And I only have about 10 or 15 minutes, so I will transition a little bit to that. So that was sort of the highlights of this Vellvm project. And as of about 2 years ago, that was kind of where we were. As part of the DeepSpec project, we wanted to take a step back and say, where could we improve on this? So what were the bad things about all this? Well, I and Zhenzhou were both novice Coq users way back in 2012, and our proofs are incredibly clunky and horrible and not very easy to let anybody see. You can get all of it, but I would not recommend. So the Vellvm development is available, and you can take a look at it. It's probably a bit rotted because it was for an old version of Coq and so on, but it wasn't great. And so it was pretty hard for other people to adopt this, although we did have a couple of people, in particular, Gil Her at Seoul National University has been using our Vellvm infrastructure for some projects there. There were other, besides our novice behavior in terms of being Coq developers, we made a lot of other bad decisions in the design of this semantics that, in hindsight, we can fix. So things like just the way we represented the semantics and the way we structured our proofs and so on made it non-modular and hard to deal with. So that made it both difficult to deal with changes in Coq, which has evolved. I believe when we started this, the type class support in Coq was not very good, and LLVM itself, our original version was for LLVM 2.6, which is quite out of date by now. And so sort of creating this monolithic code base was not a good, it was great for prototype and demonstration of possibility, but not good if you really want it to be useful over time. So I think that is actually the worst, the worst thing. But the other thing is there were a lot of ugly things we had to deal with, and some of these are still ongoing active areas of research. So LLVM itself, throughout those changes, has added many, many complicated features. Some are target specific or even language compiler specific, like tail call optimization for Haskell support or Haskell calling conventions. It also added different notions of undefined behavior. So between then and now, they added poison, and now they're thinking about removing undef. So tracking those kind of changes has been hard. And there's still a lot of semantic issues at these kind of low levels. So things like undefined behaviors due to uninitialized variables and ill-typed casts and things like that. And then there are many other properties. And our original approach, which I think is still pretty sensible, was to kind of separate target-independent things from just insane bad behaviors and deal with the left thing via non-determinism and the right thing via just being stuck in the semantics. And that's okay, but dealing with non-determinism everywhere is a real pain, especially for these proofs. So we're looking for ways to deal with that. And yeah, lots of thorny semantic issues. Okay, so in the last few minutes, I'll say about where we're coming since Vellvm is part of DeepSpec. So first of all, the part of the so this is where the transition is a little bad because I'm cobbling together many talks. But part of the motivation for the Deep Specifications project, which is a big joint project across at Penn and Princeton, MIT, and Yale, was that when we started looking at these developments like Vellvm, this notion of a series of microtransformations it's the same thing that they're doing in the in the Certicos project, where they have 47 layers of abstraction between their low-level OS and the high-level statement of the theorem. So how do we deal with that kind of a proof engineering in a way that scales and is still performant? The other thing that's interesting, of course, is that lots of these different projects are giving essentially semantics to different kinds of systems in a programming language way. So you treat your database system as some kind of language that has an operational semantics and so on. And so how can we kind of develop methodologies across all these things? And this has led to the inspiration that maybe we can build our Vellvm semantics in a much more modular, reusable way, and make it easier thereby to adapt to changes in either Coq or to the LLVM and so on, or to experiment with different possible memory models as the LLVM community decides to change things for different concurrency semantics, for example. So we've been seeking a way to make this more modular and kind of connect the things we're doing in Vellvm to all the other DeepSpec projects. And from the point of view of everything I've been saying here, Vellvm itself is just one particular instance of a semantics defined by a kind of program representation and parameterized by some interactions, in this case with, say, the memory model, which gives a behavior to the various operations in the LLVM core. If you look at the other DeepSpec projects, they also have similar kinds of structures. And the thing that connects them is that they're differing systems, but they have a common way of abstracting the behavior. So when we took a step back and looked at what kinds of things do we need to express the semantic properties of Vellvm versus, say, the EST proofs that they're doing in the verified toolchain versus the semantics they're using in Certicos or the fiat-generated optimal databases that MIT is working on, we actually realized that we had a kind of common common structure that we had started to adopt, which is actually well known in the functional programming language community. And we've sort of adapted this for use both in Vellvm but also in other DeepSpec projects. And that's basically this idea of an interaction tree. And since I only have 5 minutes, and probably many of you will already appreciate this, I'll just kind of sketch the idea, and then we can wrap it up, and I'm happy to take more questions later. But basically, we're looking for a Coq methodology to represent interesting system behavior of the kinds that might be both applicable to Vellvm and also things like a web server or a database. And so we need a kind of general notion of computation that is well-behaved and has good properties and is usable in Coq. And we settled on was essentially an adaptation of these freer monads that are known from the functional programming language community and quite closely related to things like algebraic effects. So here's the basic setup for that. So this is pretty low level, and so I apologize for people who aren't Coq aficionados, but basically this is a data type that we use to represent computational behaviors in a kind of parameterized way. So I'll walk through it. It's a co-inductive data type, which in Coq means the potentially infinite stream in this case. So a system behavior could be a potentially infinite series of interactions with its environment. It's going to be a monad, which is familiar from the Haskell world, parameterized by the sort of interactions that you can do with that monad. And these are typed in the sense that you specify the results that you get back from the external interface. and these computations yield some value x. And otherwise, it's essentially a free monad construction. So you can, this is pure, or you can return a value. More interestingly, you can generate some visible event, which you should think of as an interaction with the external environment. And what does this look like? Well, there's some existentially quantified return type, y, and an event e, which says that you're going to get one of these y's, and then a continuation, which tells the sort of internal computation how to process the y and yield and continue the behaviors in this monad. The one wrinkle compared to what you would do if you're implementing this in Haskell is we need a way to allow for divergent computations that never interact with their environment, so while loops that while true do nothing. And so we have this kind of hidden internal step tau, which you should think of as sort of a hidden step of computation that's not observable from the outside world, but is useful for making sure that you can write interesting computations in this language. Okay, so this is kind of a picture of what these things are. Basically, they're infinite trees where these green boxes denote interactions with the outside world, and you get a response from the outside world and apply the continuation to that response. They can terminate with some answers by returning, and then by encoding various things in the return type, you can add errors and layer monadic effects on top of these things. So why do we like these? Well, it's a monad, so that's great. It has some nice notions of behavioral equivalences that are very connected to the kinds of simulation proofs we were doing in the original Vellvm. So you can define strong bisimulations and weaker bisimulations up to tau, and is also extractable in the sense that you can extract this to good code that you can run from Haskell or from OCaml and to get interpreters and things like that. Yeah.
How do you define a bisimulation in this presence of these existentially quantified events where you don't know, like it?
Yeah. So let's see. Basically, the bisimulation is quantified over all inputs you might get from that event. And if you need to refine it, so the strongest bisimulation would say, for all inputs, you get the two continuations. For all inputs I, K1 of I and K2 of I have to be in simulation.
So I guess I'm asking actually a more basic question, which is suppose you have two actions and you want to say they bisimulate and they're both about to do an event, but because the return type of that event is existentially quantified, you don't know that they're the same types on both sides. So do you assert that they're Leibniz equal?
The E in the event is still there, so that you would know the E, and the E has a unique return type. I can show you the code maybe after we're done if you're curious. But since we're getting almost to the end, I should wrap up. Okay, so anyway, the high level is we're at this very moment, we're in the process of building a Coq library for these interaction trees. You can find them if you go to DeepSpec/interaction trees on GitHub. And we're also in the process of porting our new Vellvm semantics to use, well, we already are using them, but the way, just to give you a sense of how that works, is we kind of pick the right interactions for our LLVM code, in this case, various memory model interactions. And then we can instantiate that monad and implement our behaviors as kind of monadic interpreters of this trace. And I'm going to skip over a bunch of stuff because, so this is all sort of details about the memory model, but you can tie it to an interpreter in the way that you normally do with a functional programming language. I'll just say that to give you a sense, like our deep web, which is a verified web server, uses something akin to this interface. I think it's not exactly this anymore, but basically we need to specify, say, a socket API, and we can do that as well. I guess that was the higher level network API. This is more like the OS level POSIX sockets interface, which you can imagine writing C code against. And part of this library that I mentioned we're building lets you do more sort of fancier things with the IO specs. So you can write combinators at the event level to sort of add errors or instrumentation and so on in a kind of nice way. So that's something that's quite exciting at the moment. There's a lot of technical challenges with doing any of this in Coq. Co-induction is a pain. Some of the basic proofs are surprisingly tricky, but we found lots of uses of these things in DeepSpec. One cool thing is they also work well with the quick-chick style testing methodology that Benjamin Pierce is working on. So you can, since you can extract and run these things, you can write test cases and even generate the test cases automatically. And we have cool things to say about that. So I will just leave this work in progress slide up while I finish. So we're working on this interaction tree stuff. Vellvm is very much in progress. This sort of new Vellvm is very much in progress. You can find that on the Vellvm GitHub. And I'm happy to talk about any of this in more detail. And thanks for your attention. Sure.
What would you change about LLVM to make, specifically to make the formal modeling easier?
I would put a saner undefined semantics would be the #1 thing, I think. There is some hope that maybe that's going on. I think that's probably the biggest thing. The other thing I would change is I would make the type system meaningful as opposed to meaningless, which is, it's not quite meaningless, but it's got a very, very weak type system, and they should either eliminate it because it's kind of verbose and useless, or they should actually make it useful. So those are my two biggest beefs about LLVM at the moment. They also change things a lot, so that's hard to do for formalization. But our strategy there is to kind of hope to carve out kind of a useful, stable subset that will not change over time as much, we hope. Yeah?
I'm sorry if you already mentioned this, but what is DeepSpec?
Yeah, sorry, I went through that very quickly. So DeepSpec is the name of this research project, which is an NSF expedition. So it's kind of a 5-year big research project that's basically people at Penn, including me and Stephanie and Benjamin Pierce, Andrew Appel and Leonard Berenger from Princeton, Zhang Xiao at Yale, and Adam Chapala at MIT. And basically, we were jokingly, when we were writing that proposal, calling ourselves the East Coast Coq users group, because it's basically like the Acela corridor of Coq users, so Penn, Princeton, Yale, MIT. And we all have these projects that are kind of related, doing formal verification of code, interesting systems in Coq. And we thought it would be useful to try to distill scientific principles about how we can do better specifications, how to connect these different kinds of projects and do formal verification at that level. So yeah, happy to tell you more about that if you're interested.
Makes sense.
Yeah.
For your interaction trees models, that captures, I think, the program behavior. For your property specification language, do you have thoughts on that?
Yeah, you mean like for properties of the programs?
Of the interaction trees.
Yeah, so actually, one thing that's kind of interesting is we can think of interaction trees both as implementation and specification in certain ways. So by having a refinement relation. And in fact, I didn't go into it all, but one of the things that's going on at Princeton at the moment is basically, so they have this verifiable VST, verifiable software toolchain, where they're using kind of a separation logic to reason about C programs. And the technique that you can use to connect it to interaction trees is basically treat the interaction tree as sort of part of the ghost state that you can reason about as the program behaves. So for example, with the socket API I showed you, you could sort of connect the actions of a call to the OS open function with an interaction tree ghost state that says, I've done this open operation. And you can sort of push that through the logic, and the cool thing is then you can connect that tree to a Coq level, purely functional implementation of something and show that they're related somehow, and therefore kind of lift the level of abstraction from C to a pure function in Galena, which is how we're trying to do some of the specification for our web server stuff. Yeah, so I'm pretty excited about the interaction trees at the moment. They're cool data type. I guess Haskell people might not be so excited because they're probably there. Yeah.
So the interaction trees, what's tricky with them is sometimes when you start messing. Like
Yes.
handling exceptions and stuff.
Yes. I think that is true. We have, so Gregory Maleka has also been involved in these interaction trees, and he has observed that you can treat some kinds of effects compositionally. So not everything. I'm not sure you would be able to do the effects handlers in that way, but things like treat recursion as an effect, you can kind of work out in the semantics, which would let you take sort of two functions that are mutually recursive, give them denotations that are separate of each other in terms of interaction trees, and then basically merge them together, like link them together semantically and get a new interaction tree that describes the composed behavior. So I haven't thought about effects handling or exception handling, but maybe something like that would work out. So we could do it for some recursion, things like that. Yeah, but you're right. There is this issue if the effect itself isn't some monad, then you run into this.
Yeah, I mean, you should allow events to contain computations.
Yeah. Yeah, then you get then it's harder. Yeah, that's true.
Let's continue discussions over lunch. Thanks.
Yeah.